So hey everyone, welcome back to another video on the F110 autonomous racing course. And in this video, I'm going to walk you through what you need to do for your next assignment, which will be using the ROS F110 autonomous racing simulator. So last week we released the instructions for how you can get access to the online version of the simulator through logging in with your UVA account, and passwords were also shared with each of the teams. And I got some queries, if you're not on the UVA network, how can you still get access? Then for that, I recommend you go to F1tenth.dev and just download the standalone version. Now, bear in mind, the standalone version is a little bit compute heavy, so it may run slowly on your virtual machine. So I highly recommend you use the online version for which the instructions were shared. So this assignment in a nutshell is going to be about programming your virtual F110 car of your team. This is a team assignment such that it can go around this track that we have set up multiple times using a very basic algorithm called wall following. So essentially, as the name implies, you will just follow the profile of the walls of the track, whether it's the inner or the outer wall, or you can track both of them, and you want to keep a certain distance away from your reference wall or the combination of the two. And so in today's video, I will first discuss the algorithm, just a basic intuition about how can you use the LiDAR sensor to accomplish this, kind of what you see in this loop video playing on the slide. But then I'm going to walk you through what you actually have to do for the assignment. We have provided some template code as a part of a new race package that you will download and tinker around with to complete that template. And then in the end of this video, I will switch to the virtual machine and actually show you some code as well, just to orient you and get you started with this assignment. So with that in mind, let's jump into the first part where we'll just discuss this wall following algorithm. And so the idea behind this wall following is that we will only use the LiDAR as the primary perception sensor in order to go around the track autonomously. Now, previously in the lectures, we have discussed concepts like scan matching and now even simultaneous localization and mapping as a way to map the environment using scan matching. But for this assignment, you are not going to build any map, nor are you actually going to even estimate the position of the car. So this is a purely what one can call a reactive method, where we don't even need to track where we are in the world. We just need to react to the sensor data from the LiDAR in some clever manner that results in a behavior where we can autonomously go around the track as many times as we want, accomplishing this wall following algorithm. And so the idea in a nutshell is the following. You have your car next to a wall, and we assume that the requirement is that you want your car to always be some distance d away from the reference wall, right? So this is some user-defined input that you provide, and you want the car to always maintain this buffer between its own position and the position of the wall that it's tracking. And so the question is, well, how do you, make sure that this reference is always tracked, or you maintain this capital D distance away from the wall? So let's look at some very basic geometry. The idea is that at any time, let's say our car is, not aligned with the axis parallel to the axis of the wall. And not only that, it's not just that it's offset from the parallel axis, it's actually misaligned. It's facing in a different direction, as you can see in this picture. And so here's an algorithm, or a very basic idea, that in the frame of reference of the car, so remember how we spoke about base link and the other transforms in a previous lecture. So if you look at the origin located at the sensor on the car, what we do is we pick two LiDAR rays. So the LiDAR is going to give us 1,000 or something values for each specific angle at which a laser ray was sent and received. And so what we are saying is that we choose two rays which face the same side as the side which we are tracking. So in this case, the right side. So those two rays are shown in orange. And so in this picture, just for the sake of argument, one of them is at 0 degrees with respect to the axis of the LiDAR. So it's in the same plane as let's say the y-axis is this and the x-axis is the forward one. So one is at 0 degrees, which is this one, and the other is some theta degrees from 0, or the first ray, right, which is this second one over here. So we pick these two rays, and what the LiDAR scan message is going to tell us is the distance b and the distance a corresponding to these angles of 0 and theta degrees. And what follows from that is just basic geometry, that if my car is in a pose alpha away from the original heading, which is the parallel to the wall heading, then I have this relationship that in order to compute my distance from the wall, the true distance from the wall, which in this case is AB, AB is given by B times cosine of alpha, right? From this triangle right here. And so, but we don't know what is alpha, and from geometry, you can convince yourself it follows that alpha is the tangent inverse of this expression, which depends upon A, which is given by the LiDAR, B, which is given by the LiDAR, and theta, which is your design choice. Okay, so convince yourself. You can pause and do some paper and pen, old school writing to convince yourself that this relationship is true. And so once we know alpha, then we know AB. And so AB is just the cosine component of this distance B to the wall. Okay, so why do we need to know AB? Because our goal is to keep our car at a distance capital D from the wall. So we need to know at any time how further apart laterally are we from the wall on the right hand side. And that's why AB is the measurement of that. So if you know AB, then one can say that the error between your desired trajectory, which is the distance capital D from the wall, and your current trajectory, which is AB distance from the wall, is given by this expression. Right? So it makes sense that your error is just a difference between what is your current distance to the wall and the desired distance to the wall. And so if you can steer your car in a manner to reduce this error, then you can get back on track. And at the surface, that seems like a good idea, but this actually is not going to work, right? Why won't it work? Because AB is the distance to the wall right now, right? So when we compute this error, this is the instantaneous error of our desired trajectory minus our current distance from the wall. So if we just fix this instantaneous error, we will always be chasing the true error, because it will take you some time to fix this error, but in that time the error has already changed. Right, so in the next time step, the distance is not AB, whereas you were still trying to fix or steer with AB as the distance in mind. So a better thing to do is not to compute the error as the instantaneous value, but instead do a very simple geometric trick where you assume a constant velocity and you project the motion of the car along its current heading into the future, right? So currently my car is at A, and let's say at time t equals k, my car is at position A. I don't know the coordinates of the position of this point A, neither do I need it for this algorithm, because all I compute at time k is this distance, is this measurement AB from the previous equation. However, at time k, I am projecting the car a certain distance, let's say L, along the same axis or along the same heading as is currently given by the car, right? So we know alpha at any point. We can project the car in the future by a certain distance, a fixed distance, or a fixed velocity times time. And what I want to minimize is not the instantaneous value of the error between the desired trajectory and AB, but I want to minimize the error between the desired trajectory and this future projected error, which is given by CD. So at time k, I am projecting my car into the future, and I'm going to minimize the expected error in the next time step or in future rather than the instantaneous error. So that way I'm not always chasing the error. I actually have a chance of, in the next step, reducing the error to 0. Now, yes, given their assumptions on how you're doing this projection, we may not exactly reduce the error to 0, but it's still better than minimizing the instantaneous error. So what follows is that the same math holds where AB is given by the cosine component of this 0-degree ray, and CD is given by AB, which is the previous calculation, plus AC. AC is the distance of projection times the sine component of alpha. Okay, and we know alpha from our choices of the rays that we picked. And it is appropriate to use the error that we are trying to minimize to track this fixed distance from the wall as the desired trajectory minus CD, okay, not AB. So keep that in mind, that when you are doing this wall following algorithm, you are essentially picking two rays looking in the same direction where the wall is that you're trying to be a certain fixed distance away from. This fixed distance away from the wall is your desired trajectory in some sense. And then what you are computing at every time step is based on those two rays that you picked and the geometry which follows. You compute a future value of the error where you have projected the car some AC or some L distance in front, and that's the error you are going to try to minimize. So I hope that's clear in terms of what the basic math of wall following is. But now let's talk about how do you actually use this value of error to steer you along this desired trajectory, right? So remember, the goal or the output of this algorithm would be that you can always adjust your steering in a manner that you maintain this desired distance away from the reference or from the wall, this reference distance away from the wall. So if you have heard about proportional, integral, and derivative control or PID control, then the next part is just going to be a refresher. If not, then don't worry, I'm going to describe that in just a second. But the idea is the following, that what we can say is, we can say that the correction in steering is proportional to, so this is some constant of proportionality, it's proportional to the current value of the error, which is given by desired trajectory minus CD in the previous time step, plus another proportional constant KD, or a derivative constant, which is proportional to not just the absolute value of the error, but also the rate of change of the error itself, right? So DET by DT means you are looking at the error at time t minus the error at time, say t minus delta or t minus 1 upon the value of time, which is delta. So this is like a derivative component. We are not only interested in reacting to the current value of the error, but we are interested in also reacting to the rate at which the error is changing. So this is what is called proportional integral derivative control, where your control signal, so this is our control signal that we will send to the car, which will be in form of a steering correction or a steering value as well. And so the steering correction is proportional to this proportionality constant. So it's proportional to the error, it's proportional to the derivative of the error, and this expression is missing the integrative term. We'll talk about that in just a second. So this is actually just PD control and not even proportional integral derivative control. So this is just the same expression expressed in the much more legible format, non-mathematical format. So once you have this steering correction computed, and the goal is obviously to tune your controller with appropriate values of KP and KD, which work for the track. Because error is something that the previous math will give you, but KP and KD are unknowns. So you have to try different values and see how the car responds. And once you have this V of theta, which can be thought of as steering correction, then you simply say that my current steering angle is my previous steering angle adjusted with my error correction. Okay, so this is the update equation This is the update steering equation. And in combination of these two things, what will happen is your car moves, it always computes the value of this projected error based on this previous geometry, and it steers itself in response to the error, and in this case the derivative of the error, and continuously adjusts the steering value so that it can track the reference value, which is a certain distance away from the wall. Okay, so you have to implement this algorithm in the simulator, and then let me show you some more examples of the effects of these proportionality constants, and then we'll talk about a little bit about the code as well. But first, let's take a detour and get into understanding PID in the context of wall following. So remember, the objective of wall following can be distilled into two sub-objectives. The first is we want to keep the car driving along a certain distance away from the wall. So in this picture, let's assume we want to keep the car driving on the center line of this hallway or the track. Remember, the track has walls on both sides so that the LiDAR can get some clean signals. So that's requirement one. And the second requirement is I want to at all times be parallel to the walls, or more or less parallel. I know during the turn, you cannot be parallel to a long stretch, but instantaneously you are parallel to the curvature during a turn, and during a straight, you always want to be parallel to the left wall or the right wall, or in this case, you're tracking both the left and right wall because you want to be on the center line. So what does this mean for us? So here is an example where you are parallel to the wall, but you are not on the center line. So your desired error is, let's say, this capital D, but your projected error CD is going to be just this value. So you will have to, in this case, steer left based on your PD controller. Here's an example where you more or less on average are on the center line, but you are not parallel to the wall, right? Sometimes you face here, sometimes you face this way, and so on. So we want to do both with the single algorithm. And so what we are trying to do is, in a little bit more detail, let's assume that we have the axis X and Y, which is aligned with the center line. And so this requirement to keep the car driving along the center line can be just expressed as that we want Y to be 0. That's right? So if Y is 0, that means you are on the X-axis. And the requirement that you are parallel to the wall means that this heading offset theta or phi, I think it's theta, this theta is also 0, meaning you are parallel to the wall and along the center axis. So if you satisfy these two requirements, then you are fulfilling the control objective in this case. And so to do so, what we can do is the same trick as the following. We want to say that we don't just want to satisfy this instantaneously, but we want to compute our error, expected error in the future. So we project the position of our car some distance L into the future. And then we can say what we want is not that Y is not only that Y should be 0, meaning that you are on the blue line or the center line in this case, or the desired trajectory, but after driving L meters, you don't want any horizontal offset, right? So you want this L sine of phi to also be 0, which means AB should be 0. Okay, so don't get confused with this generic notation. This is just repeating what I've already said, but in this case, instead of using specific LiDAR rays, we are speaking in generic terms on what the control objective is. So we want L sine phi to be 0 and Y to be also 0. Okay, so assuming that when we project in front, we are assuming that we are holding the velocity constant. And this is usually a reasonable assumption because the sampling time is so small that velocity will not drastically change. So the goal is, how do we control the steering angle, because velocity is constant, so we only have to worry about steering. How do we control the steering angle of our autonomous car so that we can meet both of these objectives? And so here I postulate that the error can be written as the sum of these two components. So we want y to be 0 and L sine phi to be 0, and we add a negative sign in front, which I'll explain in just a second. But you can say we want both of them to be 0, so this is my error term at any given time. Why do we add a negative here, and why does this work? Because let's consider this example. When y is positive, meaning your car is towards the left of the center line, that's the y positive, we want to steer right, meaning we want our phi to be less than 0. And similarly, when L sine phi is positive and we are left and we will be left to the center line, so this distance is over here, you are facing this way and you are away from the center line, we want to steer right as well. Therefore, we can set the steering to be some value proportional to the error term. And now you can see why we added the negative here, because steering right in this nomenclature and in this setup means that this phi would be negative, because you remember how phi is starting from the axis of the car. So if we want to steer right, we have to go this way, which means it's negative phi in this coordinate system. So when the car is on the left hand side, our desired correction would be towards the right, and that checks out because of the way the error is set up. And you can verify similarly, when the car is to the right, we want phi to be positive, so the correction is positive in this case. Why would it be positive? Because in this case, both the y and the L sine phi would be negative themselves, so this expression would be positive. Okay, so in a nutshell, we want our correction proportional to the error. So that's why we can say that my steering is some constant of proportionality times the error itself. And what we did earlier was that, what if the error is increasing quickly? We may want the controller to react quickly as well. So not only do we want it to react to the absolute value of the error, we want it to react to the rate of change of error itself. And that's why we apply a derivative gain. So my steering correction is my proportionality constant times the error, plus a derivative constant times the rate of change of error, or the derivative of the error. So this is the derivative component of the proportional integral derivative term. And in general PID, the integral proportionality constant would be a constant here, ki here, which is proportional to the accumulation of errors. So you sum up the errors over some horizon in the past, and you also react to that. It's the integral of the error term in some interval window of time t. So you are reacting to the instantaneous error, which itself is being computed by projecting the car. So I use the term instantaneous, but it's really looking at a future error. So you react to that error term, you react to the rate of change of that error term, and you also react to accumulated errors over some time t. So to minimize some drift that might get accumulated over time. So that in a nutshell is what PID controller is. And in your code, and I will show you the code in just a bit here, you have to tune these errors, mostly the proportional and derivative, but I think there's integral errors as well. You have to tune them for your track, for your algorithm, for your desired distance. So let me visually show you the effect of tuning these gains. So these proportionality constants are sometimes called the gains of the PID controller. And this is for the real F110 testbed. So these values may not work exactly for your solution in the simulator. But if we set the proportional gain to be 14, we have no integrative gain, and we have some small derivative gain. Here's what that looks like. We want our car to be in the center line of this hallway. So we define the left or the right distance away from the wall. And then the PID is going to look at the A and the B rays. It's going to compute its future projected error and use a proportional derivative controller to keep us on the track. So let me play this, and you can see how the car instantaneously almost like converges to the center of the hallway. And there's a warp in the video because it's being filmed using a handheld camera. So this is when your gains are well tuned. This is the kind of behavior you expect to see in a straight hallway. When the gains are not well tuned. So let's, for the sake of example, we reduce the proportionality gain. So in the previous sort of optimal value was 14. Here I'm reducing the value by almost 1/3. So before I show you the result, what do you expect is going to happen, right? Everything is still the same, but only the proportionality gain has been reduced from 14 to just 5. So what would we expect is going to happen as a result of that? And if you think about it, what was the role of the proportionality gain? It was getting multiplied by the value of the error itself. So you can think of the KP, or the proportionality gain, as the parameter of your controller which governs how sensitive are you to the value of the error itself, because it's getting multiplied by that. So in other words, when this value is high, you are very sensitive to the error, meaning you will correct, the response you have will be much sharper or much stronger steering correction, because the value of KP gets multiplied by the error. And so if we reduce the proportionality gain, what we anticipate will happen is you will be slower to respond to correcting the error. You'll be your sensitivity to the absolute value of the error is going to be much lower than the optimal case. So that's sort of what we also see pan out in this real world demo, where when the car has a less proportionality gain, you can see it oscillates out and about the center line before ultimately kind of getting converged with the center, because it's reducing the error, but the gain is not high enough for it to make a strong correction to the steering value. And finally, if we add some integrative gain, I want to think about want you to think about it. Integrative gain is the gain of your controller which accounts for accumulated errors. So if you are already offset, or you go offset and you bump up this gain, you will be very, very sensitive to this error. And so you might overcorrect in terms of your steering correction. So here's an example of that. You can see intentionally the car has been placed not parallel to the wall. It's still kind of on the center line, but it's not parallel to the wall. So there would be, when you project along this, let me see if I can draw on the video. So if you project this car some distance into the future, let's say we were tracking the right-hand side wall. So we want to maintain this distance D from the wall, but my future projection would give me, this distance, CD away from the wall. And so I have to sort of, adjust for this offset theta, which I'm already in my initial state, I'm there. So what that means is the integrative gain will start looking at this large value of error, because it's just, the error is persisting over time, and it will overcompensate for it because we are multiplying it by some large value. And so as a result, what you see happen is the car just actually overcorrects and just crashes into the wall. Right? The other gains are not able to compensate for this behavior. So that in summary is what the wall following algorithm is, and this is sort of what you have to implement in the simulator, but it's very equivalent to implementing it in the real world. So let's jump into the actual assignment itself, and I'll walk you through the logistics of what templates have been made available, what do you have to actually do and demo, and then I will switch to the simulator and show you some stuff. So first things first, what we have done, as is usually done for all the other labs and assignments, for the course repository, we have added a new package called Race, and this package is going to be used as the basis to develop your code for wall following. And so one of the things that you will do is you will SSH into your Teams account, the simulator account, the access of which has been shared last week, and you just have to, git clone this URL, or if you already have that there, just do a git pull to get access to the race package. And you're already used to it, so I won't dwell too much on this. So what is this race package? It has a bunch of different files available for you that will help you in this assignment. First of all, we have defined some custom message files that we will use. Maybe not all of them, but we'll use at least one of them. And then the main assignment is you have to complete these two nodes. You have to complete a ROS node called distance_finder, and then you have to complete another node called control.python. And the scan test is just like a testing code to make sure everything is working fine before you start editing the actual two templates. So one of the custom messages that you will use is what is called the PID input message. And it will compute the value of the steering error and also velocity error. I'll talk about velocity error in just a second. And so this message is used by the error topic that you will publish and subscribe to, and that's how the two nodes that you have to write use this. So let me give you an overview of what actually is happening or going to happen for while following. How do these nodes talk to each other? So here's a very high level view of the online simulation setup. You have your host machine. So this is your sort of host Ubuntu machine with ROS melodic that you should have hooked up to the UVA VPN account or VPN network, sorry, and be able to view all the ROS topics and do teleop like we did last week. This is our simulator in the cloud, and the simulator is running a virtual F110 car in this environment called Gazebo. Okay, and so what you have to do is the following. You have to write a node which will reside on the sim itself. So this is not going to reside on your local machine. It will be in the Catkin workspace of your Teams account on the simulator. And so what this node does, as the name implies, it's going to find the distance of the car from the right-hand side wall or the left-hand side wall. So it will subscribe to your team name.scan topic, which, as the name implies, is the topic on which the LiDAR messages of your virtual F110 car are getting published. Be sure to subscribe to your team name topic as well, and not to some other team, because I know these topics are visible. So even by error, you can subscribe to someone else. Hopefully, intentionally, you don't subscribe to someone else. It doesn't help you, because you need to control your car, and doesn't make sense to subscribe to the scan messages of another car. So you have to subscribe to the scan messages, and we've discussed this before. The message type is of laser scan. I'll show you what the different fields of laser scan are. And then you use this laser scan to do this exercise of picking the two rays, computing your error term, which is the projected distance minus the desired trajectory distance. And you publish that on your topic called team name/error, where you have to obviously replace team name with your actual team name, team alpha, bravo, Charlie, so on. And this topic called error is using our custom message type that I showed you previously, which has the two fields that you can publish error on velocity, and you can publish the error term for steering. Okay, so this is the job of distance.finder. It subscribes to laser scan and it publishes the error. So since it is publishing the error, who is listening to this topic? That would be the control.python file. The control.python node is going to subscribe to the team name error, which is getting published by your distance finder. And no points for guessing what it will do. It will implement the proportional integral derivative controller using this error term. And what it does is, it computes the steering. You have to compute the steering angle and the velocity and pass it to this team name multiplexer command. So this topic, which is unique to your car because it is suffixed by team name, is going to accept values of the steering angle and the velocity of your virtual car, and then your car will respond and move autonomously with these inputs. Now, these values that you pass to the command are of a specific message type called Ackermann message. So remember how we discussed what are Ackermann steering and differential steering robots. So I will show you what is this Ackermann drive message that you have to construct in your control node and pass it on. In fact, we'll show you that in the template as well. Okay, so once you pass this command, you are done. What is happening internally is that the F110 gazebo simulator is reading this command and moving the car. Okay, so that's what's happening underneath the hood, but you don't have to do that. You only have to publish the right message. So let me go over a little bit more detail on both distance finder and control.python and what you have to actually tweak in both of these files. And then I will switch to the actual simulator and the code. So the distance finder, as I've said, subscribes to the laser scan message, and the goal is to publish to the error message. So in the code, you will find that you need to complete two functions. One function is called getRange, and the other is the callback function. So you can guess that the callback will be invoked every time we get a new scan message, because that's associated with the raw subscriber. So let's look at, every time a new laser scan message is received, the callback function is invoked. Now within this callback function, there is another function called getRange. And this getRange function is actually computing the A, B, and the CD of that diagram that I showed you. And it's computing and then the callback function is computing the error, and we are publishing this error of the message type PID input on this topic called team name /error. Okay, so in a nutshell, in the callback, you choose the two rays corresponding to some values or angles in your field of view of the LiDAR. And you specify, corresponding to each of those angles, which values of the range do you want to use, which is the value of, if you remember in the figure, the value A and B, which correspond to, let's say, the 0 degree and the theta degree ray. So you have to do that in the code. So you will get the A and B and the two angles. And the function which does that is called getRanges. Okay, and then you calculate these distances and the offset alpha. So you calculate alpha, AB, and CD using the knowledge AB and theta. Then you calculate error as your desired trajectory, which would be declared as a variable, constant variable in your code, minus the future trajectory. And you compute the error. You can compute two values of the error. One is the PID underscore error field, which you can think of as the steering error. And you can also pass some version of this error as the velocity part of this PID input message. And then you simply publish this message. So this is sort of the pseudocode of what the callback function is doing. And once you look at the code, this will make a whole lot of sense. But you have to fill in this getRange function. You have to do the geometry and the computation to calculate the error itself, and then package it into this custom message type called PID input, and publish this to your team name /error topic. So within getRange, the idea is that it takes input the scan data, because this is part of the callback function. So you get scan data and you get some desired angle, which is the value of theta. And what it outputs is the distance reported by the LiDAR at that angle. So if you pass it 0 degrees in our figure, it would output A. If you pass it, let's say 30 degrees or some other value, it outputs B. And I'm using A and B consistent with that figure. The thing you have to also account for is sometimes you may pass at some angle and there is not good data available. So you have to account for any extremities or missing values in your data field for certain angles. Okay, so this getRange function has to be able to deal with any scan data that is received. Okay, so that's the idea behind distance finder. It is publishing this error message, and this is getting subscribed by the control node, which is the second node you have to complete. Okay, so the control.python ROS node, it subscribes to the error topic that you are publishing. This error topic again is of the message type PID input. It has two fields. One is simply called error and the other is called velocity that we just showed you. So every time, since this is a subscriber as well, every time a new message is received, a new error message is received, it will call its own callback function. And in that callback function, you are going to implement the or compute the steering correction using PD or PID control. You're going to update the steering value. You will do some sanity check for that the value that you compute is within some desired range, and you will publish this value to your team name /multiplexer /command. This topic is visible for every team. This is the topic. So this topic is visible for every team. This is the topic on which if you publish your steering angle and your velocity, the car will start moving in response to the values that you publish. So I told you earlier that this has a specific message type itself, which is called Ackermann drive message. So here is the structure of the Ackermann drive message, which is used by this command topic for your team. You only care about two fields, the speed and the steering angle. The rest you can set to 0. And you have to provide values which are between -100 and 100 for both of them. So we are not providing the value of speed in some miles per hour or meters per second, right? This is not what's happening. What is happening is +100 is full throttle, -100 is full brake or reverse. Similarly, +100 for steering is full steering right, -100 is full steering left. And so you are always providing this value in this range and publishing it on the command topic using this message type called Ackermann drive. And so when you import some dependencies in the control.python, you will see one of them is this message type. And that's already, I think, provided by default in the template code. And on top of that, you will create a launch file called autonomous.launch, which will launch all of these nodes in sequence in the correct order. And it will also ask for the user inputs for the proportional derivative and integral gain, and also the constant velocity input as well. And another thing I encourage you to compute is that in the template code and in the assignment, the PD controller I discussed, it's correcting the steering based on this lateral offset or the distance away from the wall, right? The velocity is being held constant. What we want you to also attempt to do is, can you write a control logic such that the velocity also changes with error? Meaning that when you are on a straight part of the track and the error is small, you can go faster. But when you have to make a U-turn or some sharp turn, the velocity decreases proportionally to kind of the turn that you are doing, or the error, the value of some function of the error term. Right, so the concept that I explained about steering also applies to velocity, and we encourage you to also do velocity PID. Okay, let me give you a quick example of how some of the kind of tools and techniques and sort of tips for this assignment. I should say that both the slide deck and a handout for the assignment are linked in the description of the video, so you will have access to all of this. But here's sort of one way to think about how would you do this. So you have to verify this, but I'm just using an example that the LiDAR in the sim has a 270-degree field of view, right? So it goes from kind of 0 degree or plus 135 degrees. 0 is actually here. It goes from plus 135 degree to negative 135 degree. Right, so it has a total field of view of 270 degrees, and it has a range of, let's say, 30 meters. So the first thing you have to do in your distance finder is subscribe to the scan topic for your team name /scan for your car. And so this is of the type laser scan message, and this is the actual laser scan message definition which is part of this sensor messages package that you already have installed in ROS. And so you can, inspect things like the min and the max angle, the increment, to figure out this, which is the 0-degree ray, the 90-degree ray, so on and so forth. The thing that you will use the most is this ranges array, right? So from the min to the max angle, in some fixed increments, it will publish the values of the distance reported at that angle, and that is aggregated into this array of 32-bit floating point values called ranges, right? So laser scan outputs this data structure, and we will mostly be using the ranges to compute many things. So here's the same cartoon again. Let's say I have this horizontal ray, and it's not at 0 because the LiDAR field of view is such that this is actually 30 degrees. So I would pick my first ray at 30 degrees. I would pass this to get range, and it will return some value A, which is the range at this array, at this ray. Then I will choose the value of theta in my picture, and that will give me the new angle at 80 degrees, and I will send that to get range, and I will get the function, get the value B. And then using A, theta, and B, I will compute alpha, AB, and CD using the geometry that we discussed. And so what you want to do is implement a very basic logic, right? So how do you get the values of A and B? You simply read it out from the range array. So I'll give you a very simple example. So we can define that the index, so remember, range is an array. Let's say this array has some length, or the number of values in this array is given by the length of the ranges. So what we can say is, what is the per unit index? It is the total length divided by the number of values, or the field of view of the array itself. So this should be actually not 240, but let's say 270, because that's my field of view. And so then I can just say, for a 30-degree, for the range at 30 degrees, I want to find the value of the index I in my range vector such that that value corresponds to the 30-degree ray of my LiDAR. And so this is a very simple math to get to that value of index, or figure out what I is, right? So my what I'm calling my 0 ray index, it's 0 because it's aligned with the axis of my base link. It would be 30 times this length divided by the field of view, which would be simply given. We can simply read it off as that would be the index of the ray, which corresponds to 30 degrees. And when you read off range dot 0 ray index, it will give you the value of the range reported at that ray. So this is subject to 30 degrees in this case. Okay, so this is just some understanding of the range vector itself. And there's a separate script called the scan test in the template, which goes through this. Okay, so what you have to actually demo is the following. So remember, in the simulator, your car starts somewhere over here in this pit lane, let's call it, or the paddock area. And so you will begin your demo in such a way that the car moves out, makes this left turn, keeps going straight, even though there's a gap here, it keeps going straight. So in some sense, my advice would be to follow the right wall if you want to do that. Then makes this turn, again maintains some distance away from the right wall. It goes all the way around, following this profile of the track, goes all the way around here and back, and then makes a right turn. So you have to be clever here. Remember, here you made a left turn, you made another left turn, you made another left turn, you made another left turn, but now you are making your right turn. So you have to be careful. and then you keep going here, and instead of coming back into the pits, you continue and do another lap. Okay, that's what you have to do. So once you exit the pits, you're not coming back. You just have to show at least 2 laps around the track using ideas of wall following. Obviously, you can do other stuff as well, meaning that you can have a high level definition file which says after making 3 left turns, we know that the next turn is right. So I might switch from tracking the right wall to the left wall or something like that. Okay, so that sort of creative freedom is available to you for this assignment. But this is what you have to demo. There will be a live demo, meaning we will have teams log on to the server, and together with the TAs, we will run your code live and see the behavior of your car in a live virtual online session. But on top of that, you have to obviously submit your code as well, because we will verify the correctness of your code. So that, in a nutshell, is the wall following assignment. It's a very exciting assignment. It's also the simplest thing you can do in the simulator, but it'll take you some time to tune these PID values and make sure you are scaling the error terms appropriately, and so on and so forth. So with that being said, I will now switch to the code part and the F110 simulator, and walk you through the code first very quickly, and then show you how you have to actually push your code, and even show you some template examples of the race package. So let me pause and jump to the code, and then I will resume this video. Okay, so here, let me just give you a quick glimpse of where the code is. So this is our F110 Course Labs Git repo, and so we've added a new race package. As I've said before, we'll use this custom PID input message. It's a very simple data structure for the message type. And then in the source subdirectory in the race package, we have provided 3 kind of helpful nodes. First is a node called scan test. This is just to test that you can subscribe successfully to your team's scan messages. And I'll run this node in just a second. And then the 2 nodes that you have to complete are distance finder and control.python. So very quickly, let me, without repeating everything I've already said in the slides, just show you how this code is organized. So we are importing a bunch of different stuff to ensure that we are importing the laser scan and the custom message definition as well. So if you look at this this file, it's doing very straightforward stuff. We first initialize a node. I highly recommend that you also change the name of your node to have the suffix of your team name, right? So just an example, if you're team alpha, I suggest you call your node team alpha distance finder. So even though you have your own Catkin workspace, all the topics are visible to all the teams. So we just don't want to avoid any confusion. So this node is called team name underscore distance finder. And what it does is it's subscribing to this topic called team name scan. So this has to be your team name. I cannot emphasize enough. That's why I read through all these comments, which are provided to make sure you're not subscribing and publishing to the wrong stuff. So you subscribe to scan, and for every scan message, you get a callback function. So let's go to the callback. So the input to the callback is going to be this laser scan data. You pick a value of theta. You have to change this. This is just something to initialize it. You get the value of your the distances at theta and at 0 degrees, or in this case, the 0 degree could be actually some non-zero value, like I showed you in the example. 0 means the horizontal ray, which is in line with the base link rear axis of the car, right? So which is also shown here, that the actual angle may be non-zero. So you do that, then you you can change into radians. So here you have to compute. By the way, this function which returns the range, you have to fill this as well, right? This is the index of the array in the range vector, the stuff that I just showed you at the end of the presentation, and you have to account for observed values. Then you have to write the math to compute the A, B, C, D, and alpha, and then compute the error itself. I've already provided the code to package and publish the error message. So you can, you just have to say, you just have to say you just have to provide the values of this error and velocity terms, which will be packaged into this. And we will publish this because this node is publishing on team name error. And you have to change this, right? The topic shouldn't be called team name error. It should be team alpha bravo, so on and so forth /error. Okay, so and that's essentially what this node does. It subscribes to laser scan and publishes on its error topic. Then the control.python is following. And so what control.python does is, let's go to the bottom. It first will ask the user to input the values of the proportional and derivative gain. So already it's a big hint from the template that don't worry about integral gain for this assignment. You can do the demo just using proportional and derivative gains. And so you are echoing these commands. You are soliciting the values of KP, KD from the user. And then again, I suggest you name your controller according to your team name. This is subscribing to the error which your previous node distance finder was publishing. And so for every value of the error received, we go to the callback function called control, which is defined here. So control reads the value of the error. There's a variable provided to assist with the computation of the differential part of the error. So you can keep track of your previous value of the error when you have to do the differential gain times the difference of the error from the previous to the current value. And so here you have to write the code where you scale the error, you apply the PID equation, and then you compute the steering value. And once again, what you have to do is you have to package this value and publish this onto the Ackerman, team name /multiplexer /command. And so you have to probably change this part of code to make sure you are publishing the Ackerman Ackerman drive message format. I don't think this is the correct code, so you may have to change this and package your message where you publish the speed and the steering, but you publish this to your Ackerman drive format. And so you have to do that here as well. You have to set up a publisher to publish to team name multiplexer command topic. And this topic will use this message type, which we discussed in the video of this assignment. Okay, so this in a nutshell is what you have to do. You kind of have to just fill in the blanks, but it'll take you some time to stitch everything together. And most of the time, I believe, would be spent in the high-level logic of how far apart from the wall do you need to be, how do you adjust your velocity. Remember here, the velocity is just some arbitrary value. It's no special value. You are expected to change this for your demo as well. Okay, so not that complex, but just it will require some time to get this going. And if you have any doubts, as always, feel free to ping us on Piazza, and the TA and I will jump on office hours and clear all your doubts. So the last thing I want to show before I finish this video is just some example of logging into the virtual machine and getting access to your simulator. And also maybe we can run the scantest.python file together. And I'll show you how you can replicate this for your own team account. So I'll pause one more time and then we'll resume once I'm logged into my virtual machine. Okay, so I'm now logged into my virtual machine. It's connected to the UVA VPN network. And if you followed all the instructions that we shared on how to access the online simulator, then the host file and your ROS master, everything should be set up. And you can see how this prompt also appears that this instance of the terminal from my local VM is already connected to the sim. I can always verify that by running ROS topic list, and it should connect to the simulator even though there is no ROS core running on my local machine. So you can see how all the team topics are visible to all the teams, which is why I emphasize that we should pay careful attention to the topic names that we publish to, just so that we are not publishing to other teams' topics or some generic topic name. So if you look at each of the team, there are so many different things which are getting published, and it's easy to kind of get lost in what is useful versus what is not. Most of these things are being published because of the Gazebo simulator. So as you can see, just to give you some idea, we have topics which you can use to access the camera, simulated camera. We have topics which independently tell you what is happening on each of the wheels and the steering as well. But for this assignment, you only need to worry about two topics, right? So the first is your team name scan. This is the topic on which laser messages are published. And then the second is the team name and multiplexer. So let me find that, and command right here. So this is your topic on which you will publish the Ackerman steering and velocity messages to actually move your car in the autonomous mode. So these are the only topics of interest for the wall following. Just to give you a quick idea, we can even try to see these topics. So let me clear, and you can say ROS topic echo, and I can say team, let's say alpha, just for the sake of it, and scan. So we should see some scan messages from the LiDAR. So you can see these messages are being echoed because the LiDAR is running on the track. Okay, let me clear that. And so once you are able to connect and see all the topics, you can always bring up the visualization. So you can do that by saying ROS launch. Name of the package is F1tenth sim visualization. We have a file called racecar.visualization, but you need to provide some arguments. So the first is computing ID with a colon equal, and this is my computing ID. And then you want to also provide another argument called team name. And in this case, I'm going to actually try to connect to the instructor machine. So I have a team name which is different from like team Alpha Bravo Charlie. So this is a special name that the instructors use. I believe it's called team name instructor demo car. Yeah, let's see if that works. Okay, so here we go. The instructor car is not yet in the starting position. So we can actually fix that. Remember, we can fix the starting position of the car by running resetting the ROS parameter. So let me do that. But to do so, we need to first log into the account or the team workspace, right? So remember, there's a workspace on your local machine, but there's also a workspace on the simulator assigned to every team. And in fact, to do the assignment, the control nodes are publishing messages. That code is residing on the server. It's not being controlled through your local machine. You can use your local machine for code development, but ultimately you have to push that code to the Catkin workspace on your team's account. So let's do that, right? So let me launch a new instance of a terminal here, and we'll use this terminal to SSH into your team account. So I'm going to use my account. I believe that's instructor at ROSmaster. You would use your SSH team name at ROSmaster, and okay, that should work. And there we go. So you can see how the shell has changed from my virtual machine to now I'm logged to the lab machine with the instructor account. So as first order of business, let me reset my car. So the command to do that is ROS parameter set, and we have a TA instructor demo car, and we wanted to reset to pit stop 1. That's the command, and there you go. All of a sudden, my car is back to my home position. So I think this is a good tip to ensure always, even in your launch file, you reset the car before starting off. All right, so this has nothing to do with wall following yet. So let's jump into what you may want to do after you have SSH. So if you look at the current kind of a directory structure in your account, you will see the Catkin workspace has already been created. In fact, this has some nodes which you use for teleop during the lab session for the simulator. So what we will do is we will first pull the race package into the Catkin workspace in the simulation account assigned for your team. So to do that, let's jump into the source. We should go into Catkin workspace source. So we jump into the source subdirectory, and here I want to say let's say git clone, and then we say https github.com linklab uva, and the repository is F1tenth -course labs. Okay, so it has pulled the code into my source subdirectory. So this one was already created. You don't have to touch or mess with any of that. And I've just pulled the entire repository into this folder. So no points for guessing what's next. We should compile it. But before that, I actually want to go into the F1tenth course labs, show you that there is a race package. And if you go to the race package, we have a source subdirectory. Yeah, I want to make sure that all my nodes are executable. So you can just do, we can even do it one at a time. Doesn't really matter because there are just 3 nodes. So let's make distance, and then the final node is the one I want to show you as well, is scan test. Right, so if these appear in this green color, then it means they are executable. Okay, so let me clear everything. Let me now go back to my root folder, which is Catkin workspace. And now, since I've added a bunch of new code, I'm going to run Catkin make. Okay, this is going to make the race package along with other beginner tutorial and stuff that we've used in the previous labs, but we will not really need any of those per se. Okay, so it built successfully without any errors. This is what you should also see in your instances. And so now I want to show you how to ensure that this template code is going to work for you, right? So let me again, by the way, as a exercise, I should say source Catkin workspace devel setup.bash. You should source your environment, remember always, because I don't know if it has been included in the bash RC yet. So what we can do now is we can navigate to the code that I just showed you. So F1tenth course labs, the package is race, and in the source folder we have the 2 templates that I already showed you, but now we have another file called scantest.py. So let me open this file. So I'm going to say nano scantest.python. So it's a very simple node. What you see is we are importing a laser scan message type, and we initialize a node. This node is called, let me just call it Instructor _ scan test, but you should name it, Team Alpha or Team Bravo scan test. And it is simply subscribing to the topic scan for your team. So in my case, that is TA instructor demo car /scan. So this topic is already present in ROS, and this node is subscribing to that. What is this doing? It's for every scan message, the callback function, it is simply reading the particular value of the range. In fact, this is the central value of the range. And I believe the midpoint of the range vector should correspond to the distance in front of the car, directly in front of the car. So we should see, roughly what this distance to the front wall looks like when we execute this. So I'm happy with my edit. The only thing I had to change, and you'll have to change this for your scan test as well, is replace the template token name with your team name. And so let's just save that, and yeah, we write it back to the same file. And ideally, since we changed a piece of code, we should run catkin make again. Now you may not have to do this because it's just a Python script, so you can see the make didn't really do anything new, but out of habit we should always do this and source the file as well. So now if everything works, I should be able to say ROS run and package race and then call scantest.python. And what I should see is just a single value from my LiDAR scan, which corresponds to the distance in front of the car, assuming that that center value is aligned with the longitudinal axis of the car. And it seems that's about right. So it's giving me this consistent 3.5 value, which is what this distance might be. Okay, so the scan test is nothing but a way for you to sort of figure out whether you can subscribe successfully to your team's scan function or scan topic, because that's very important for you to attempt the rest of the assignment. Okay, and we've already covered how you will use this information to get the range from the right hand or the left hand wall, and then use that to do the PID for your controller. Okay, so that's all I really wanted to show you, give you a quick glimpse of all of this is happening on the sim workspace. The local workspace is only for visualization. You can't control anything from your local workspace. You have to be SSH'd into the server for making any changes to the car itself. So let me stop here, and that's in a nutshell what the wall following assignment is all about. I hope you have a fun time doing this assignment. It's a very interesting but slightly challenging assignment. As always, I will see you next time. We will continue some of the material on localization and advanced methods for autonomous racing. So I'll see you next time. Thanks. So one more thing I want to attempt to do is show you that the other side of it. So I just showed you the perception side with scan test. What we can try and do is try and control the car directly and see what happens, right? So let me attempt this. I'm going to say ROS topic publish. Remember how we had a publisher, and we can say I want to publish a message at the rate of 1 message per second. And so TA instructor demo car, I want to publish to the topic multiplexer command, which has the message type Ackermann drive. And there you go, right? It's already giving me the fields to edit. So let's just do very basic stuff and say I want the speed to be 25 and everything else is 0. And what I think we anticipate will happen is the car should move forward. Okay, it's too fast. It almost did a wheelie, but you get the idea, right? So this is what you have to do when you do the publishing of your control command, right? So you have to publish to this topic called team name multiplexer command, which uses this message type, which has all of these fields. I only use the speed field, but you have to publish both speed and steering angle, both of which should be sent or provided by your control.python. So quite an extreme example. So we've all learned a lesson. 25 is maybe too fast, but nevertheless, I just wanted to show this last piece of the publisher from the control node as well. So yeah, now we can end this video, and I'll see you next time.